why do we know it has to have at least 4 zeros? We have 3 terms, right? 3 extrema. And remember the maximum, by the way, I had it plugged in so you can just zoom in because I think that battery's almost dead, isn't it?
Is it?
Miles? How many minutes does it say it has?
33.
Yeah, go ahead and leave it plugged in, just zoom in from back there. It's not ideal, but it has 3 extrema, right? So if it has 3 extrema, the degree has to be at least 4. But how many x-intercepts can we see? 2. So what do the other 2 have to be? Imaginary. So you can't see the imaginary extrema, or the imaginary zeros. But the idea is, I know it has to be 4th degree. What's up?
How do you make the camera zoom?
I don't know either.
There's literally a little slide on the top.
This thing?
This thing right
Yeah.
there? Oh, that makes sense.
Oh.
Yeah, they don't want to zoom in that much. All right, play around with it till you can see well. So again, like the idea is, hey, I have to have at least 4 zeros here because it's 4th degree, but I only see 2 of them. So the other 2 have to be what? Imaginary. So it's not that you can create and see imaginary zeros. It's the idea that I know there's 4, but I can't see 2 of them. So there we go. Okay. I'm going to come back to this identifying domain intervals in a minute because that's a more complicated thing. Okay, possible number of extremes just by looking at an equation. Possible number of x-intercepts. I'm going to tie that into the in behavior over there. So, I already collected these, so I'm going to just hold on to it. Okay, I'll use one of these problems though. And this way you can go back and look at it later. So 5x to the 7th plus 3x to the 4th minus 2x squared minus 1. Now, possible number of extrema just by looking at the equation, possible number of x-intercepts. Guys, that's what we explicitly did with the mathematic activity for a whole day, exploring that concept. We've done a few practice problems like that in class. Make sure that we study this. So what is the number of extrema and the number of x-intercepts tied into? Like what tells us those things?
Degree.
The degree. The degree here is what?
7.
7. My highest power. So what's the maximum number of extrema?
6.
Okay, where are you getting that from?
Degree minus 1.
It's n minus 1. But what do we know about extrema? They come in pairs. So it could be 6 or 4 or 0. Right? They come in pairs. There's my max, and they come in pairs. That's it. If you can identify your degree, you can identify how many extrema it could have. All right? Possible number of x-intercepts.
7.
Okay, where are you getting 7 from?
Degree.
The degree, remember, the degree is 7, so it has to have how many zeros?
7.
So 7 zeros. And all of those zeros could be distinct x-intercepts. So 7 x-intercepts is possible. But what else can happen with zeros that would cause us to have less?
Double roots.
We get a double roots, right? So 1 x-intercept counts as how many zeros?
1, 2.
That's 2, right? If it's a double root, it counts as 2 zeros. So it could be 7 or it could be 6
5.
or
5.
5, because we could have 2 double roots, you could have a triple root, you could have 2 imaginary zeros, right? All of those would reduce my number of x-intercepts. Or
4, 3, 2, 1, 0.
not on this one. Sometimes it could be 0. But I want you to remember,
Oh my bad. Okay.
think about your in behavior here. So this ties into this question. First off, what determines in behavior? We got a whole bunch of crap going on, right? But what's going to determine my in behavior?
Leading coefficient.
The leading coefficient and the
Degree.
degree. It's an odd degree. So what do we know about the in behavior? It has to be
Opposite.
opposite. It has to be different, right? And overall, is that opposite in behavior decreasing or is it increasing?
Increasing.
That's a positive, right? So it's got to be increasing. That's it. And so, remember, I always tie it back to a line. That's why I drew a line here as a dash thing, because a line is what degree? First degree. So you see how that's an odd degree? So all odd degree polynomials are going to have the same in behavior. That's it. All odd degree polynomials are going to have the same in behavior. You have a check?
I was doing Big City warm up.
Warm up, got it. So, has to be opposite in behavior. So, and then this leading coefficient is positive, so it's got to be what? Overall it is increasing. Now, is 5x to the 7th actually going to look like this?
No.
No, heck no. Because the in behavior doesn't care about the middle, it just cares about the ends. So it'd still have this in behavior though, just like that linear. So it could look something like this, 1, 2, 3, 4, 5, 4, 5, 6, 7. Right? Notice how I have 7 zeros in there, right? 1, 2, 3, 4, 5, 6, 7. That's again why it could have 1, 2, 3, 4, 5 x-intercepts and still be 7th degree. Okay? So what I do is part of my evidence, like I don't try to do this in my head, like I've started to be able to picture these graphs in my head, but I could quickly sketch something like this that would look 7th degree, and that would be part of my evidence for my in behavior. But notice, the reason why I say it has to be 1, if it's odd degree and it goes in opposite in behaviors, that means it has to go from negative to being what? And what do you have to intersect to go from negative to positive? The x-axis, those zeros.
Can we have Danielle Hunter to the office remote, please?
She's on her way.
Thank you.
So there has to be at least 1 0 with odd degree. Does there have to be 1 0 with even degree? Or sorry, 1 x-intercept. Does there have to be 1 x-intercept with even degree? No. Right. Notice how I drew it all above the x-axis. All of those zeros would be imaginary. So you could have 0 x-intercepts. What are your questions about extrema and zeros? Or x-intercepts from that information? Going once. Going twice. Sold. Okay? In behavior. Notice if you have a sketch like this, it's easier to see. On the left-hand side, what's x going towards? Negative infinity. And as we go to the left, it's also going down. Quick sketches like this, 1, are great evidence, and 2, help you visually see what's happening. On the right-hand side, what's happening? As x goes towards positive infinity, what's y going towards? It's going up to positive infinity. Sketches of those graphs can be really instrumental in helping you see this, thinking through what it's going to look like. Does that also answer 3 part C? Why it could be 7 or 5 or 3 or 1 x-intercept? I will point out they're going by pairs, but only extrema go in pairs. For part 3C, 7, 6, 5, 4, 3, 2, or 1 x-intercepts. So keep that in mind. Is that, I don't know whose question was, does that, okay. So to me, it's a make sure sheet. Here's that. How do you sketch a graph? By just looking at the characteristics. Just make sure the graph has the characteristics. I'll give an example of that in a second. Determine a sketch of a polynomial is impossible. So well, let's look at number 6 for that question. Question 6 explicitly says that we want an odd degree. So give me an example of an odd degree. N could equal 7, or it could be 5. It could be anything, right? The next statement here is that we have 3 relative extrema. So this is the first issue with this one. If it's 7th degree, how many extrema could it have? 4.
0.
Yep. So could it have 3 relative extrema?
No.
No. If the characteristics contradict each other, they're not possible to happen at the same time, then it's an impossible graph to do. The second statement was as x goes towards negative infinity, y goes towards negative infinity. As x goes towards infinity, and actually it says f of x goes towards negative infinity, but notice that means that the end behavior, is it the same or different? Different. Notice they're both negative, that means they're both going down. Is that possible with an odd degree? No. Those characteristics contradict each other. If characteristics contradict each other, they can't happen at the same time, it's an impossible graph. Okay? Does that explain that question that we had?
So we're not supposed to draw a graph on it?
Well, if it's impossible, how do you draw a graph?
You can't.
If it is impossible, then explain why with the directions, right? Yeah, if it's impossible, don't draw a graph because you literally cannot do it. The other one over here says degree 4. It says 2 different real zeros. Is it possible to have just 2 different real zeros?
Yes. Yes.
Yes? Yeah. There's a couple ways that you can make this work. I'll show you a couple in a second. And then it says as x goes towards negative infinity, f of x goes towards infinity. And as x goes towards infinity, f of x goes towards infinity. That means on the left-hand side is going up, and on the right-hand side is going up. The end behavior is the same. Does that fit with 4th degree?
Yes.
Yeah. Okay, so then I would sketch out a graph that has those characteristics. Whoops, too much. Notice only 2 different real zeros. They just both have a multiplicity of 2. Right here, this 0 has a multiplicity of
2.
3. If it goes through like that, this is a multiplicity of 1. 2 different real zeros, right? Still has 4 zeros. There's also the option, because I didn't make it clear I would accept this. It has 3 extrema, right? But it has imaginary zeros, because I only see 2 real ones. All of these would be acceptable. There's no one right answer. And even these, they can be moved around a little bit. All it has to do is fit those characteristics. And then possible equation, it could be anything as long as this has what kind of leading coefficient? Positive. And the power is 4, or the degree is 4. That's it. That's all you have to do, is create something that meets those requirements. If they're both going up, my leading coefficient has to be positive, and my degree has to be 4. That's it. Does that answer these questions that we've had so far? Because I've mostly answered this side of the room. Good? Okay. How can you determine end behavior based on the equation? So we good on that now? Yes? The last question was about domain intervals of increase, decrease. Let's see if I can find an example in the slides for today. So please make sure, remember, it's about a learning process. One thing I would make sure I do is I go back to my definitions, always. Precise understanding of definitions and vocabulary is actually critical to being understanding math. So like, I know there's a common misconception of, oh, I'm not really a math person, or I'm better at English and at history. But the fact of the matter is like, mathematics is a language, and so if we focus on the language, for those of y'all who are more comfortable with languages, and you think about the vocabulary and you understand the vocabulary, and then you think about the story the math is telling, it's the same as history, just also has more numbers focused on it. There's a story, there's a relationship, there's a pattern here. That is something that everyone can learn and be successful with. We just got to, for some of us, get out of our head of saying, hey, I'm a math person or I'm not a math person. And I know that we have to move fast, and I hate it. I was literally talking with someone this morning at the gym who used to be an assistant principal over at SIPSI and high school, and she's now working on PhD at UA, and we were talking about the issues of a block. Like, I hate the block system. Like, you have to learn everything in a single semester. That's garbage. Learning takes time, and that's not effective for student learning. That's the same thing I told central office when they proposed this, and they ignored my literal pages of explanation of why this was a bad idea, and here we still are. But I'm not salty about it. Task today. So reflection, I already talked about that. Remember, please take that reflection home, responding to the things I've given you questions or thoughts about, and you're going to turn those reflections in on Tuesday, not Monday, because yay, we have Monday off. Okay. And Mary, you need one as well, right?
Yeah.
So, Mary, don't let me forget to pass back some papers that I have for you. Here's that. Whoop, sorry, I'm just destroying your foot there. There you go. So, those reflections due Monday. Give you a nice little freebie grade for that. We're going to wrap up lesson 3 and 4. Possible combinations of, oh, I forgot to take that off. We did that yesterday. Graphs and equations of functions from characteristics. We're going to play with that some more. And constructing polynomial equations from zeros or roots. I gotta make it a little bit quicker. So. If you, let's see, for this set right here. At the end of today's lesson, or the video of today's lesson, I'm going to go through and do a short video working through. So like if you look at the video on YouTube from today and look at the end of it, I'm going to work through these and add it on to the end of that video. So if you need help and so try it first. If you're not sure about your answers, check against what I post. If you want to come in and ask questions Tuesday, you can for this. Because we need to focus today on these ideas, especially for those of us who are struggling with it. Domain intervals of increase, decrease. We just talked about possible degree and leading coefficients based on the graph. Make sure we're providing evidence. We'll talk about some of those things again on Tuesday. And I will say this. I was looking at what Elizabeth was doing with her domain intervals of increase, decrease. Guys, what do you have to identify in order to figure out your domain intervals of increase, decrease? What do you have to identify in order to get your domain intervals of increase, decrease? It's something else on this proficiency scale right here.
Extreme.
So which points?
Extreme.
Extreme, right? Like a relative max is quite literally where the function what? Stops increasing and starts to
decrease.
The foundation is those extrema. A relative minimum is where the function stops decreasing and starts to increase. You've got to identify those extrema, and that's what Elizabeth made notes of, and she was asking me about. Like, that's it. You got to look for those things. I didn't mean to leave this one in here. I hate this question. Okay, see these two. Let me come back to this in a second. Oh yeah, we got all this today. Oh, there we go. All right. So if you want to get out your what page is this? Page 263. This does not ask for the domain intervals of increase, decrease, but I'm going to go ahead and go over that part with you. Okay, so page 263, maybe 264. And that'll be our last question from the, yes sir?
You want me to stop it? You want me to stop recording or keep it going?
Keep it going. Yeah. Okay, so page 263 or 264. Yes, ma'am. What's up? Yeah, starting with any equation. Just consolidate to one and trash the other. Oh, you don't have the other. Yeah, it should be one that's starting with the equation and one starting with the graph table. I have copies of them somewhere. Don't let me forget to look for them. Oh, here you go. All right. Yep. So let's look here. I'm going to color coordinate because, man, it makes things easy. So one thing I want to point out, I'm going to look at the slope of that tangent line. Remember, that's what it's all about. Is that, ooh, there's no way that shows up well. Does it? You look what? All right. So notice I'm going to draw a tangent line in here, meaning it touches at how many points? Right, that one right there. Not 2, 1. Okay? Slope of that tangent line, positive or negative? That's a negative slope, right? So what's it doing through here? Notice you can label things like this to help as well. I'm going to come back and add the other things in a minute, but notice right here, what's it doing here? That slope is positive, so it is increasing. Here, negative slope, so we are decreasing. And through here, increasing. Positive slope, so increasing. That's the foundation to being successful here. Was that right, page 263? Okay. You don't have that page? That's what I'm saying. Say it, let's see if it's out of order or something. I don't know. We'll have to try to find it later. Alright, so we have decreasing, right? Interval of decrease. That's where I'm going to start because I read from left to right. So where does this function start to decrease? Remember, like I would point out, it's always what through here? Decreasing. So what x value, and remember we want domain values. Do not put y values, put x values. When we are talking about intervals of increase, decrease, I told you the most common mistake students make is they write those y values in there, but I already know it's decreasing on those y. I want to know where it's decreasing, what are the domain values, and so what's the lowest x value where it starts to decrease? And then comma. And where does it stop decreasing? At the what? Well, just in general, what do we call this? Relative minimum. Literally, a relative minimum is where it stops decreasing and starts to increase. So what's the domain value there? -1, not half, -1 and a half? Be careful, -1/2 would be right here. -1.5. You said -1/2. -1/2 is right here. Be careful. It's a common thing, misspeaking like that, but -1.5 here. Notice that's in between -1 and -2. Maybe -1.6, I don't know. But somewhere around -1.5. So Kristen, what's happening after it stops decreasing? It starts to increase, right? So where's it going to start increasing? What is it? Remember, literally a relative minimum is where it stops decreasing and starts to increase, right? Stops decreasing, starts to increase. So it's got to start increasing there. And then where does it stop increasing? At a relative maximum. And then don't forget, do I want the x or the y? I want the x. Where does it stop increasing? That's a 1/2. And then after that relative maximum, what's it start to do? Decrease. Where does it start to decrease? 1/2. And then where does it stop decreasing? At this relative minimum, 2.5. We good with that? So please note, and I'm going to just finish this up really quickly. 2.5 to infinity. Intervals of increase and decrease always change where? At extreme. Second, what are the only types of values you use with domain intervals of increase and decrease? Only report x values. Remember, that's why I add that extra word in. It's implied, but most people don't ever talk about it that way. They just say intervals of increase, decrease, but I'll read it out if you need me to. But most people just say intervals of increase, decrease, but it's the domain intervals of increase, decrease. Is that easier to see now? Yeah. I don't know why, but these show up better in the light, whereas the expos show up better with that background in the dark. It's weird. I've never used these markers before. But I got new markers coming in today. Depends on how quickly we go through them. I need to buy like several more boxes. The vast majority of my teacher money goes towards markers. Yeah, yeah. Questions about those intervals of increase, decrease? So, where do the intervals change? Extrema. Literally the definition of the relative max is where it stops increasing, starts to decrease. Relative minimum, where it stops decreasing and starts to increase. And Peyton, what are the only types of values we report on those domain intervals of increase and decrease? What are the only types of values we report on those domain intervals of increase and decrease? Domain intervals of increase, decrease. It's domain, so just the x values. Remember, we only found x values here, right? Do not report the y values. Don't do it, don't do it, don't do it. I know it's the most common mistake, so I harp on it. Just don't make that mistake, it hurts. Questions before we continue? You're gonna crush it in the future, right, Davis? Yeah, you already crushed it, right? Miles, why you giggle like that? Why you have such little faith? What? Yes for dang back. That's not what I heard. Alright. I want you to do one practice problem here. With your small groups of vertical surfaces. So this is going backwards a little bit, but page 242, I'm going to give you 2 minutes to come up with a sketch with these characteristics, or if it's impossible, to explain why. Okay, so 242 is what I have up here. So page 242, part C. Yep, 242, part C.
Okay, how many out here?
2 minutes. 242. It's going backwards quite a bit. I skipped that. Thank you. Thank you. All right, so let's talk about this one because I'm looking around the room and I see some of us doing some things very well with this one, but there's a couple of things I do need to talk about. So a lot of us came up with it's not possible. However, there is one concerning thing looking around the room. I'm going to talk about why it's possible or not in a second, but you can't really see the yellow over here, but I want you to see this really quickly. Odd degree, I love the note, 3, 5, 7, something like that, increases to x equals -3. Now, when I look at this, is this increasing to x equals -3? Because it looks to me like it's increasing to x equals 0. If it says it's increasing to x equals -3, what does there have to be at that line x equals -3? Well, if it stops increasing and starts to decrease, it's got to have a what? Extreme. So it's increasing to here. Like when I look at this, it has to increase to x equals -3. Now, you can make that maximum y value 4 there for sure. Okay? But please notice, if it says it increases to x equals -3, it's got to have a maximum there. And it can have some other stuff, but let's make it simple. After that increase, it starts to what? Decrease until x equals 3. So there needs to be a relative minimum there. Because if we don't have a relative maximum and minimum at those x values, then it's not increasing to that point and then decreasing to the next one, and then what has to happen? Increase. Like that's, at the best, what we should have done to start here, but why is this actually impossible? What did y'all recognize or realize? It says an absolute maximum. Guys, if I have an odd degree, what's my minimum y value? Negative infinity. What's my maximum y value? So what can you not have if you're going all the way from negative infinity all the way up to positive infinity? You can't have an absolute maximum. You can have a relative maximum. But remember we talked about that. What are the only types of functions that can have an absolute extremum? Even degree. Right? It's only those even degree. Okay? I will point this out. If we are struggling with this, still, I wasn't planning on it, but I'm going to do one more of these. If we're still struggling with this after this, there are check your understanding questions that literally, it's 2 or 3 for mild, medium, and spicy that have those characteristics, okay? There are solutions on the back. I'll work through and narrate some of them over the weekend and put those out there to help y'all study next week. But do those practice things. You got to check your understanding, you got to practice it, and then if you're still stuck on sketching those from the characteristics, that's a great question to ask at the beginning of class on Tuesday. Alright, got to do our check your understanding if we're struggling with this. And I know that may sound bizarre, of like, well, if I'm struggling with it, then why do what I do check your understanding? Well, what's on the back? Solutions. Now be careful, because I will point this out, is this the only option here? With all of these, there's infinitely many options, okay? I gave a few examples of these. So keep that in mind, like, there just are certain characteristics you have to hit. If you're like, well, I don't know what the answer is, part of that is there only one correct answer? You just have to hit the characteristics. It has to have a relative maximum here on this line, it has to have a relative minimum here on this line. But again, this one would end up being what? What do we recognize? Impossible. Can't have some of those characteristics. Let me look at... Alright, I want y'all to do D. Let's do D. Thank you. Alright, looking around the room. Much better time this time around. I will make this note. A lot of us put our relative maximum right on the y-axis, right? And that's totally fine. As long as the y value is what? 3. But when I look over at the 8s, did they put their relative maximum of 3 at the y-intercept? No. Did this group over here make it at the y-intercept? No. I want to point this group out because this group did do something different, and now I kind of thought outside the box on it, so I kind of gave it away. But is what they did acceptable? Because when I look around the room, all of y'all's polynomials are what degree? 4th degree. More than likely, because it has 3 extrema. But is what they did, or what they have right now on their graph, acceptable? Why? Still has 4 x-intercepts, right? Notice it doesn't have 4 roots or zeros. How many roots or zeros would this probably have? 6, right? As long as it has 4 x-intercepts. So again, my point is, and what I want to emphasize is, for these, if you're not sure, then you're stressing yourself too much. Just make sure you fit the characteristics. Now, if I were to ask you for an equation for this function, what are some of the keys that you would have to have a possible equation for this function? What do we know? A positive leading coefficient. Both ends are going up. And if I do anybody but the aces, what degree do you have to have? Degree 4. What degree would they need to have? 6. Yes, that's it. Everything after that leading, that first term or that highest power does not matter. Does that answer some more of our questions? We feeling like we understand the concept some more?
Yep.
Okay, please understand, and again, notice how I said the concept. I didn't say master the procedure. Because one, it's impossible to master this procedure. You got to play with it. Make sure you are practicing. Once we understand a concept, if you don't practice with it, things get rough. Practice, practice, practice. All right, so I want to set y'all up for this. You don't need to grab a seat. Actually, if you want to make a quick note on this problem, this C and D, do that really quickly, and then we're going to talk about page 255. So be ready to go in 90 seconds. No. Yeah. It doesn't have to. It just had to have a relative maximum, right? So it doesn't have to go to the line. There's it either. It could have been anywhere as long as relative maximum was 3. The one thing I want to caution though is, I just forgot to mention this earlier. Yours has 4 zeros, but what does the sheet say? 4 what? Does yours have 4 x-intercepts? It only has how many? 3. So remember, it had to have 4 x-intercepts. So if you wanted to come through and then come back up for that, that would have been acceptable, right? The only thing is we don't have 4x intercepts. 4 zeros, sure. But that's why over there they had 4x intercepts, but they actually had 6 zeros. And so keep in mind the difference between x intercepts. Coming down, perfect. Yep, that now has 4x intercepts. 30 more seconds to get your notes down. Run like a wind bullseye because I'm about to go.
Run like the what?
The wind bullseye. Do we not know that reference? Thank you! Toy Story 2! Which, I was alive when that came out. I don't think any of y'all were, but...
The first one you were recording.
It went class.
Toy Story 2, 1999. None of y'all were awake. You're alive, not awake. Awake either, but... Huh? Like 95. I was like, I was 4 when the first one came out, so like, I was like, I remember that one. That and the Toy Story 2, pivotal to my childhood. Anyways, right here, y'all were alive when Toy Story 3 came out, I believe. Not. Toy Story 3, I was in college.
That was like 10. I think that was 10.
2010, you right? So yeah, I was in college. Get it. All right, so right here. Angie, or Augie, what a name. All right, so Augie, Catherine, and Chili? Is that Chili? Oh my gosh, who named these kids? Augie, Catherine, and Chili each wrote a cubic function with zeros at x equals 3, x equals 1, and x equals -4, okay? So I want you to look at these equations. Landon, come on, I need those margins to live until I get some new stuff. So Augie's equations right here. Augie said, hey, f of x equals x minus 3 times x minus 1 times x plus 4. Does Augie's equation work for those roots, or those zeros? How do we know? So we can use the zero product property. Now remember, fundamental theorem of algebra just tells me how many zeros, right? But for these specific zeros, x minus 3, once I say equal to 0, right? X minus 3 equals 0, so x would end up equaling 3, right? So that would work. But Catherine wrote a different equation. Does Catherine's equation work for those zeros? Just look at it. 5 is A, but does it still have the right zeros?
Yes.
Does the A matter for the zeros?
No.
No, Miles, what did you say earlier we could use? The what? Zero product property. If I use the zero product property here, would I still get the zeros of 3, 1, and -4? Yes, okay. So Chili said 2x minus 6, and 3x minus 3, and x plus 4. Does Chili's equation work? Why? Look at it. So 2x minus 6 equals 0. And so we're not going to like this, but notice that's 3, right? So does that 0 work? If you check this one, what's 3 times 1? Minus 3. So you try to see how it's creating a 0? So here's an important question I need you to think about, I need you to consider. If I give you 3 roots, how many different functions could you write? Not just a lot. Not just a few. Infinitely many possibilities. So not just a lot. Infinitely many possibilities. Because what's the only requirement? Those zeros. But what can A be? Your leading coefficient. It could be anything, okay? And so I want you to understand, in a second when I have you start writing these equations on your own, how many correct equations are there? Infinitely many, right? The only way for you to know exactly what the equation is, just like with quadratics, you would have to have an extra point and solve for A. And we'll do that once. But for right now, I want you to get out Actually, I can leave it on the board. Oh, that's frozen. I just want you to work on 3 of these. Actually, I'm going to have you work on 2 of these. A is lame. So I'm going to have us do B, C, and then if you finish B and C before we come back together, I want you to work on D. So I want you to write equations. I want you to write cubic functions. You only have to do 1 for B and C. If you finish early, go on to D. 3, 2, 1, break. No. Do B. Do 1 equation for B, 1 equation for C. If you get done with those early, 1 equation for D.
Oh, you thought it was about?
You want to write on board?
Is that Spider-Man? As you hold the green marker?
Yeah, the room wasn't working.
Okay. Alright, so I grab y'all's attention. Look, let's back it up and let's talk about this. Now, so first things first, I do want you to look around the room. I like the variability or variations in the way that some of us wrote C. I see around the room x minus 6, x plus 5, and x minus 6. And some of us wrote, I saw x minus 6 squared times x plus 5. I saw x minus 6 times x minus 6 times x plus 5. Do all those work? Do those give us a 0? Does this give us 2 zeros for x equals 6 with a multiplicity of 2? 100%, right? All those do. One thing I will encourage is this though. So I noticed Drake, I think y'all's group left an A in here. Just put in a number. Like don't leave it as an A. Leave it as a 1 or a 2 or they did a 5, a -3, -5 halves, I don't care. Just make it a number unless there's other requirements, okay? Now, one thing I want to ask is how did y'all get to the x minus 6 and the x plus 5? Because there's a couple of things that we could have done to show evidence here that would be very helpful in making sure we understand this long term. Say again? So reverse the zero product property. Okay, I love that. So like the 0 is x equals 6. So like what could you do to reverse the zero product property?
Subtract 6.
Subtract 6. I need it to now equal what?
0.
0. So x minus 6 is equal to 0. Notice that's now one of my factors. Remember how we said each factor equal to 0? Now we're getting a factor, or getting from the 0 back to the factor equaling 0, so I know one of my factors is x minus 6. What questions do you have about that? Okay. Notice you could have also done x equals -5, and what would you need to do to that to get the factor? I'm ignoring it, I'm going to talk to them, you chill and focus up here on what I'm talking about. X equals -5, what could I do? My factor, what could I do to that 0 right there? I could plus 5, right? Add 5. Whew. -5 plus 5 is 0. Yeah, there we go. And so notice that factor is x plus 5. But what's another way that some of us did this without having to set this value equal to the 0? Because I don't think most of us did that, did we? Set x equal to the 0 and then find the factor this way. What did y'all do? Okay, let's formalize that better. How did we use our head? What did we know that helped us get to our factors? I need more. But we just did the zero product property. There's another thing that you could have done here that focus on factored form. Hey Bella, what's the factored form of a quadratic? There's something with a 1. You say, what did you say? Did you just say 1 or did you say something else? Not just 1, because that would only have a 0 of 1. X minus, what's another word for a 0 by the way? Root, so is x minus R1. times. So remember, that's why I use R1 and R2 for those roots, right? So quite literally, if we just use that factored form, isn't this x minus R1, x minus R2, and x minus R3? Notice you can use your factored form there. That's good evidence. If you write out something like x minus R1, R2, and R3. I'll be honest, I thought or assumed that's what the majority of us were thinking or doing. Because you didn't show any work to get to those factors. So are we thinking minus the roots, or am I misthinking how we got there? Say that again. Well, no, because I just want the equation. I didn't ask for the zeros. So like what you did, zero product property, is we had the zero, right? And we rewrote this equation so that it was equal to zero, right? So we could then put that as one of my factors. Here I'm just using the understanding that my factored form is x minus R1 and x minus R2 and x minus R3. And so using that understanding of factored form to get me to the equation. What are your questions about that? What could we do, so I gotta move to the next piece of this, what could I do to get my standard form from this point though? If I was asking for it. Say again. I can distribute. And what was that thing I recommended to help you distribute? So distribute, and so distribute to get standard form, and distribute to get standard form. I recommend that area model. Now, I want to talk about B really quickly, and then D really quickly. Notice x minus R1 and x, so x minus 0. X minus R2, so x minus what? What is R2? Not 2. 2i. And then x minus R3, so what is R3? Close. Negative 2i. And so if I subtract a negative, what does that end up becoming? Positive. And does it matter what A is? No, I'm not going to sweat that right now, okay? So this is why I would understand, and don't forget your factored form, it's just x minus the roots. And if you understand your roots, your life's pretty straightforward. Now I do want to look at getting this into a standard form really quickly, because this area model is going to be really helpful here when you have imaginary numbers. So what is x times x? X times negative 2i. Typically you put your variable last, right? So I is still part of that number, right? 2i times x. I'm adding it. And then positive 2i times negative 2i. Right, squared. And so this is why I wanted to look at this one. I want to remind you, what is I squared again? Remember, I squared is negative 1. That's what allows me to square something and get a negative. And that was why I was the square root of negative 1. Remember, I is the square root of negative 1. I squared, though, is. I squared is. And so really, what this is negative 4 times negative 1. And what is negative 4 times negative 1? Positive what? 4. Notice these are like terms but opposites, so they're going to add up to 0. And so what I have is x times x squared plus 4. So I just want to remind you a little bit with that imaginary number. Huh? Maybe statistics wasn't that hard. Alright. Listen, I squared is negative 1. Don't make it harder than that. You just got to remember. Alright. Really quickly. This would only be an exceeds portion of the proficiency scale, but I do want to point out, in D, you can actually know exactly what A is. Because I don't know A, so X minus R1, so X minus 2. Then X minus, what's R2? And then X minus 1. So X minus R1, X minus R2, X minus R3. That's it. However, we also know f of 0 is equal to what? Okay. So I can plug in this for x, and this would go in for f of x. So if you have an extra point, you know how to actually find what a is. So negative 24 is equal to a times negative 2 times negative 3 times negative 1. So yeah, if negative 24 is equal to negative 6a, what does a have to equal 4? So you can actually find the a if you have an extra point. So I need you to keep that in mind. That would be an exceeds portion of the proficiency scale. That's honestly, based on what we did with quadratics, I would hope that that's something that we can do. But again, it's only exceeds, but that can help improve our overall scores if there's been a concept we struggled with. So that can get us up to that exceeds. So if you have an extra point, you can substitute that in. Questions, comments, concerns? What was that? Yeah. I meant to get a whole lot more done today. Well, we gotta take a test soon.
Well, everybody have a great Veterans Day.
Yeah. I will say this. I'm playing around with it a little bit. I'm just gonna introduce the very last concept for this unit. We're going to practice with this on Monday. I'm going to be out. That's what I said. I'm going to be out next Friday because I got to lead another workshop at a conference. So I may just let y'all have the test on Friday, but we are not going to study the entire unit all next week. We'll start the next unit. We'll probably practice and review on Tuesday, demonstrate your understanding on Wednesday, go over it, and then start the next unit. Or something to that effect. And then Friday is when you'll take your test, so that we don't waste class time. Yes? Alright. Okay. Really quickly, this concept is actually something that, yes, right, if you solve that equation. So, I will leave that up there. I need y'all, and you can take a picture, make sure you just make a note. What page was that stuff from?
256.
242. Okay. This is the last major concept that I need us to learn. This is called average rate of change. Man, why you gotta lie to me like this?
We told you 215, you said 242.
He told me 242. Alright, listen. Now, really quickly. Hey, I need y'all to just hear me on this. Average rate of change. Remember how like with a cubic had a quadratic additive rate of change overall, right? And a quadratic had a linear additive rate of change. And so we talked about these different types of rates of change. I talked about this idea of a tangent line. That's really important. But what I'm going to talk about when I say average rate of change, this is quite literally the slope between 2 points. Okay? So, if you look at the formula in the book, it says f of b minus f of a divided by b minus a. And so, if you just connect this to slope, what this really is this is the second y value minus the first y value divided by the second x value minus the first x value. So when we find average rate of change, what are you really just finding? The slope. And so, if you are ever asked for average rate of change, and again, we're going to practice this, but there are check your understanding questions. There is a Mathia thing I'll be assigning during my planning second block. But average rate of change is just the slope between these 2 points. And so the y value here is 0 minus the y value here is negative 600 divided by this x value is 4.25 minus this x value is 3.25. So guys, when you are asked for average rate of change, what are you finding? Your slope. If you are ever asked for average rate of change, it's a foundational piece for pre-cal concepts and for calculus. Average rate of change is just slope. So please note that this is on page something. What is? Wait. This is on 270 something. Okay. I hope you have a fantastic Veterans Day. Please make sure you are checking your understanding.
Mr. Kenny?
We basically, yes, you can turn that off. We've done almost everything. Hit the silver button on the back, Elizabeth.